Hi, I'm Michael Osman of Great Scott Gadgets, and this is Software Defined Radio with HackRF, Lesson 9, Aliasing. In this lesson, we will explore sampling and the phenomenon of aliasing. We'll use our knowledge of complex numbers to understand and solve the mysteries that we encountered in previous lessons. First, let's review the homework from Lesson 8. In Lesson 8, I demonstrated how to get started reverse engineering the signals from something like a garage door opener remote. And I asked you, for the homework for Lesson 8, to investigate your own remote keyless entry device. Let's go through the process with a remote keyless entry system from an automobile that happens to behave a little bit differently than the garage door opener remote that I used in Lesson 8. Instead of starting with the FCC filing, this time I'm going to just try to receive a signal from the device. I have a pretty good guess that it will transmit between 300 and 400 megahertz. So let's just try firing up a HackRF with an FFT to look for the signal. Instead of using GNU Radio Companion, this time I'll use Osmocom FFT, which is a program that should be installed if you have GR Osmo SDR installed. And GR Osmo SDR is the interface for HackRF to GNU Radio. So it should be there if you've been using HackRF with GNU Radio and GNU Radio Companion. Now Osmocom FFT starts up and it immediately displays an FFT. It's 8 megahertz wide, centered at 3.625 gigahertz in this case. Now if we want to see 20 megahertz wide, all we have to do is type in 20 million for the sample rate, and now we see a much wider bandwidth. And this will help us if we're looking around for a signal and don't know what signal, what frequency to start at. Well, I'm going to look between 300 and 400 megahertz, or really this shows me, if I tune to 300 megahertz, it shows me some below the frequency of interest. So I'll start at 310 megahertz, and now that gives me the range from 300 to 320, and I can go up in increments of 20 megahertz to find out to look for the signal that is being transmitted from my remote keyless entry device. So I'll just press the button on the device and hey, look, it's right there just below 314 megahertz. I didn't have to scroll around at all. Well, let's see. If I wanted to get a closer look at that, what could I do? I could tune to 314 megahertz. And now you can see that that is just really close to my center frequency there. I'm going to reduce my sample rate down, which will reduce the amount of visible bandwidth. Now I'm looking at 2 million samples per second, which gives me 2 megahertz of bandwidth from 313 to 315. And if I push the button on the remote keyless entry device, you can see, isn't that interesting? I see 2 different peaks. If I press peak hold, then you can clearly see those 2 peaks, not just one peak like we saw with the garage door opener remote, but 2 distinct peaks. And that suggests very strongly that this is 2-level or binary FSK, frequency shift keying. Probably this device is transmitting one frequency to represent a 0 and a different frequency to represent a 1. Anytime you see twin peaks from a transmission, that is a good indication that it's probably 2FSK. And in this case, we see 2 very distinct peaks, which is a little bit unusual for 2FSK, but it is a very strong indication that this is, in fact, 2FSK. Now, it may be helpful to know the exact center frequency, and if I hover my mouse between these peaks, it looks like it's about 313.8 or 313.84 might be about right. And if I just type that in here, 313.84, and select peak hold, I'll push the button on the remote while it's close to the antenna, and yes, that looks like it's pretty well centered around that spike in the middle. Now the spike in the middle, I'm not sure if we've talked about it much before, but you've probably noticed it. And if I scroll around to different frequencies, notice how that spike in the center is always there. We'll talk about that a little bit later today, but for now, we're going to just ignore that. And if I tune to 13.84, The important thing to note is that I'm able to get my signal of interest many dB higher by holding it close to my antenna. It's many dB higher than that spike in the middle, which means I can pretty much ignore that spike in the middle and not worry about it this time. Now, let's see what happens if we look at this signal using GNU Radio Companion. I'm going to close this Osmocom FFT window and start up GNU Radio Companion. Let's start with the flow graph that we used in Lesson 8, only this time we'll use what we've learned already and start with a default frequency of 313.84 E6. That's 313.84 megahertz. And I will save this as lesson 9a.grc and run the flow graph and see what we get. Now when I push the button on the remote, you can see in the FFT plot on the bottom, I'm getting output similar to what I got from the Osmocom FFT utility. Now on the top, if I increase my counts per division, you can see the result of my amplitude demodulation. It's showing that there is a higher amplitude while there is a transmission. But during that transmission, the amplitude stays about the same. Because there isn't any information being carried in the amplitude, the information, as we've already observed from the FFT plot, is probably being carried in the frequency. So how are we going to demodulate it? How are we going to extract frequency information over time so we can scope that instead of scoping the amplitude? Well, if you recall from Lesson 7, we talked about an algorithm that allows us to do that for complex valued signals. And here we have a complex valued waveform that instead of amplitude demodulating, as we did with the complex to mag block, we should be able to frequency demodulate it. And the algorithm that we talked about in Lesson 7 for extracting frequency information from a complex valued signal is in a block called quadrature demod, which you should know if you did the homework for Lesson 7. It's under modulators, and we will pull quadrature demod out there, and notice it's similar to complex to mag in that it takes complex valued input and produces this orange data type that's floating point valued output. The reason it produces floating point valued output is because every time there is an input sample that is complex valued, it measures the change in angle from one sample to the next, and it spits that angle out, or that difference of angle, out on its output. And an angle is a real valued number. It isn't a complex valued number. So all we have to do is remove this complex to mag block and insert the quadrature demod block in its place. Now, the quadrature demod block is unhappy because this gain setting is unsatisfied in some way. Oh, look at that. It's this very complex formula, and it refers to a variable that doesn't exist. Now, what I usually do is this. I observe that this gain parameter, all it does is just scale the output, and I don't really care about the scale of the output, so I set this to 1 and remove all of that complicated stuff. Now let's see what we get this time. Now we still have a scope plot, only this time instead of representing the instantaneous amplitude over time, it's representing the instantaneous frequency. And if I press the button on the remote, you can see things are a little bit different. I'll turn off auto range and increase my counts per division and maybe increase my seconds per division. It's a little bit messy, but you can see some things are moving a little bit. Oh, look at that. Do you see? As I've increased my seconds per division to a scale where I'm seeing milliseconds, you can see a little bit if I stop here during a transmission. Do you see how it kind of goes up and then down and then up and then down and up and then down? This, I think, is how the bits are being transmitted, but it looks really noisy. So one way that we can reduce that noise is by filtering. And we did this in the flow graph that we used to demodulate FM radio transmissions in the very first lesson. And we're going to talk about filters in much more detail in the future, but for now, let me show you a trick that we can use that is taking probably the simplest type of filter that I use all the time in GNU Radio, and that is a low-pass filter. And all I have to specify is a cutoff frequency and the transition width. Well, let's see, what cutoff frequency do we want? In other words, what frequencies are we interested in? If we look back here and I set peak hold and turn on my transmitter, we can take a look and see that these peaks are at about plus or minus 30 kilohertz. So I'm going to set my cutoff frequency a little bit higher than 30 kilohertz. Let's say 40 kilohertz or 40 E3. And then I'll set the transition width to something a little bit less than that, maybe 20 E3. And I'm going to insert this low pass filter between the Osmocom source and quadrature demod. And I'll also use its output for my FFT sync so that we can visualize what effect the filter has. Then I'll enable my filter by plugging it in or hitting the E key. And let's see what happens here. Now look at the FFT plot. Most of the noise at frequencies far away from 0 hertz have been knocked down very far. If I use auto scale, I can maybe see some of them. Nope, not anymore. It doesn't want to show me those. There we go. If I turn this way up so I see a lot of dB per division, 20 dB per division here, now I can see all that stuff way down at negative 160 dB. That's much lower than it was before. It's only the frequencies between positive 40 and negative 40 kilohertz that are being passed by this filter. Now, if I turn off auto range and increase my seconds per division and counts per division, if I look at on this scale where I'm looking at milliseconds again and press the button on the remote, hey, look at that. If I stop this, do you see how I had maybe the beginning of a packet here? There was 0 frequency for a while, and then suddenly there was a low, a high, a low, a high. This looks very much like a digital transmission. And if I look over here, yes, it looks very consistent. Let's try this a little bit more. I'll run it some more and press the button some more. And I'll increase my seconds per division a little bit. And my counts per division, maybe increase that a little bit. And we should be able to see that, look at that. Over time, we can clearly see bits being transmitted. Sometimes the frequency is low, sometimes it's high. To me, this looks like maybe 2 units of time high, 2 low, then 3 high, then 2 low, then 2 high, and then, oh, maybe that's 4 low. And we could go through and just decode this by eyeball just by looking at the output over time. And this is probably the end of a packet of information because we're low and then high, and then we're back to 0 frequency deviation. Whereas normally we're seeing a high frequency and a low frequency, each of those representing a data bit of a 0 or a 1. I'd like to draw a complex valued signal for you. The first sample is here, the second is here, the third is here, the fourth is here, the fifth is here, and so forth. And I'd like you to answer a question about this signal. It's a periodic signal. It keeps repeating these same samples over and over again. The question I'd like you to answer is, what is the frequency of this signal? Now, when I ask my students this question in person, I usually get the same couple of answers, and the most common answer I get is that it depends. The answer depends on the sample rate. And they'll say, what's the sample rate? And I might say, well, let's say the sample rate is 1 million samples per second. If the sample rate is 1 million samples per second, now can you tell me what frequency that signal is? Well, it's 1, 2, 3, 4, 5, 6, 7, 8 samples per period. It repeats itself every 8 samples. So that suggests that this should be the sample rate divided by 8, or 125 kilohertz. But what if you didn't know the sample rate? What if I never told you what the sample rate was? Could you tell me what this frequency is without knowing the sample rate? Well, you might say it's the sample rate, which is sometimes written f sub s. It's the sample rate over 8. That is a reasonable answer. Another answer that you might propose is that you could define the unit of frequency as being the angle that the sample goes for, or the angle that the signal progresses over from one sample to the next. And if you think of that in radians per sample, which is perhaps the most fundamental unit of frequency that we can think of in the digital domain, if you think of this as radians per sample, how far does this signal progress around the origin? How far does it progress around the unit circle in one sample period? Well, the amount that it progresses is tau over 8. So if you know the sample rate, it's very likely that you would express the frequency in hertz, like 125 kilohertz. But if you don't know the sample rate, the more universal or the more generic answer to the question of what is the frequency in the digital domain is to express it in radians per sample. And I like to express it as a ratio of tau. In this case, it goes 1/8 of a turn around a circle in one sample period. So the frequency is tau over 8. Now let's take a different signal. Let's say we start here, and then the next one's here, and the next one is here, and the fourth sample is here, and so forth. What is the frequency of this signal? Well, you might say it's the sample rate divided by 4, or I would just say it's tau over 4. That is the frequency of this signal. How about, let's see, how about this one? We'll go, first sample is here, and then the second sample is here, and the third sample is here, and the fourth sample is here, and the fifth is here, and so forth. Now, notice this time, we're going around this direction. We're going around clockwise instead of counterclockwise. So you can be thinking of this as being a negative angle instead of a positive angle. In other words, this is a negative frequency instead of a positive frequency. Hey, do you remember earlier one of the mysteries that we had? I think it was lesson 4. We talked about these mysteries, and one of the mysteries was, what in the world is a negative frequency? What does that mean? Well, and now we can finally see that if we're dealing with complex valued signals, a signal that progresses in the opposite direction around the unit circle can be thought of as a signal with a negative frequency. So what is the frequency of this signal? 1, 2, 3, 4, 5, 6 samples, 7, 8 times around 8 samples around the unit circle, and then it repeats itself. Well, I would say that's negative tau over 8. That's the frequency. But hang on a minute. How do we know that this signal is actually going around in the negative direction or the clockwise direction? Isn't it possible? Let's back up a minute here and look at those first 2 samples. Isn't it possible that this is a sample of a signal that actually progressed around this way 7/8 of a turn. And then if we were to go and look at the next sample, this one, well, couldn't that have been from here around 7/8 of a turn this way? Well, that's interesting. Instead of being negative tau over 8, couldn't this be positive 7/8 tau? Huh. It could be either one, couldn't it? And let's look at a different example. Let's look at an example where we have one sample here, and then the next sample here, and then the next sample here, and the next here, and the next here. It's going back and forth between two opposite points. So I would say that it's going a half turn. But is it going a half turn in this direction, or is it going a half turn in this direction? In other words, is the frequency here of this signal, is it tau over 2, or is it negative tau over 2? And I think you'll agree with me that there's no difference. It doesn't matter whether you go around the clockwise direction or the counterclockwise direction. You're going to end up with the same sequence of samples either way. In other words, there's no difference between the frequency tau over 2 and the frequency negative tau over 2. They're exactly the same. Let's take another example. Let's say that we have a signal that starts here and then is here and then is here and so forth. Well, we could say that it progressed a quarter of a tau, quarter of a turn, and then another quarter of a turn. Or we could say that it progressed negative 3/4 of a turn. And then from there it progressed negative 3/4 of a turn. So the frequency could be thought of as tau over 4, or it could be thought of as negative 3/4 tau. But guess what? It could have gone even further. What if this went, in fact, in the positive direction, one time around and a quarter? And then from here it went one time around and a quarter. Oh, guess what? This could actually be 5/4 tau. Hey, this could be any number of frequencies, couldn't it? It could be 5/4 tau. Really what it is tau over 4 plus n tau, where n is any integer number, positive or negative. That's pretty interesting. There's an infinite number of frequencies that could describe this one signal. And this is a fundamental characteristic of all digital signals. Anytime you have a digital signal that has periodic sampling like this, then the frequencies are actually periodic, or the frequency domain is periodic. And let's take a look back at the exercises, the lesson 4 homework, to look at see how this looks again in GNU Radio Companion. Here's a flow graph similar to the one we used in the lesson 2 and lesson 4 homework. If we execute the flow graph, we see that our signal source was producing a cosine wave at a frequency of 1 kilohertz, and our FFT sync in fact shows it correctly at 1 kilohertz. Now in the exercise or the homework for lesson 4, I asked you to add a scope sync to this flow graph. So we'll go in and look at instrumentation WX scope sync and add this so we can scope the output or look at the time domain representation at the same time that we look at the FFT or the frequency domain representation. And this is what it looks like. we see a spike at 1 kilohertz, and here we see what appears to be a 1 kilohertz cosine wave. But there were a few mysteries that we left unsolved at the time. One of them was, why do we have a blue channel 1 cosine wave and then a green channel 2 cosine wave that appears to be a quarter of a period out of phase from the first one, from channel 1? Well, by now you might have an idea about this, and it has to do with the fact that all of these data types are blue. And you can see that these are all set, every single block in this flow graph is set to use the complex data type. So if we're pumping a complex number into a scope sync, then we should actually see a real part and an imaginary part. And what we see here in the scope plot is the real part in blue and the imaginary part in green, called channel 1 and channel 2. So it turns out that this signal source was lying to us. It was lying to us all along about the fact that the waveform it's producing is a cosine wave. In this case, it's not a cosine wave. It's actually a complex exponential. And if you look at the XY version of this scope plot, that means it's plotting channel 1 on one axis and channel 2 on the other axis. And you can see that it plots a circle because it's going around and around the unit circle. This is what it looks like if you connect the dots. If you don't connect the dots, you can see there are 1, 2, 3, 4, 5, 6, 7, 8, and if you count all the way around, there are 32 dots in one period. That's, remember, a ratio of 32,000 samples per second and a frequency of 1 kilohertz. That's 32 samples per period, and that is in fact what we see if we look at the XY plot, which is the complex plane instead of showing the time across the horizontal axis. So what we're seeing here is actually a complex exponential, and it was all along. And there is a way to get the signal source to give us a true cosine wave, and that is to do what I asked in the exercise in the lesson 4 homework. Let's try that now. I asked you to change all of these to a float data type instead of a complex data type. Now you can go in and select the properties and switch them all to float, or let me show you a trick. If you have a block highlighted, you can use the up and down arrows to change the data type. If you highlight all these blocks and hit the down arrow once, they'll all change to orange, which is the float data type. And now we can look at the difference here. First thing you'll notice is that the scope plot only shows us one channel. This looks like a true cosine wave, not a complex exponential. Now the other thing you may notice is this FFT sync. The FFT sync, it looks similar in that it shows us a spike at 1 kilohertz, but notice that 0 hertz is now on the left. It only extends from 0 hertz to 16 kilohertz. It isn't showing us negative frequencies. And this kind of makes sense because we originally expected that negative frequencies should be identical to positive frequencies. There should be no such thing as negative frequencies for a cosine wave, a true cosine wave, or if there is a negative frequency, it's no different than the positive frequency. So all we really care about is the positive frequencies, and that's what the FFT plot gives us. Now, is there a way to get this to show us negative frequencies even though we're giving it a cosine wave and not a complex exponential? There is, in fact. As long as the FFT sync is configured to use a float data type, it'll only show us the positive frequencies. But if we were to configure it to use the complex data type, it then shows us negative frequencies. However, we have a type mismatch. We can correct that by doing a type conversion. Under type converters, you can take float to complex. And the float to complex block allows you to take two input streams, one as real and one as imaginary. So I'm going to connect the throttle output to the real input on the float to complex block and connect the float to complex output to the FFT sync. And notice that it is now happy. it's okay with me not connecting its imaginary input. What it's going to do is take a floating point number on its real valued input and then add a 0 value imaginary component and produce that complex number on its output. And then it will do that repeatedly for every input sample. And it will constantly send a stream of complex numbers to its output that have their imaginary parts always set to 0. Let's take a look at what that looks like. And I'll just disable my scope sync for now so it doesn't get in the way. Now we see the FFT plot shows us 2 peaks. We have a peak at 1 kilohertz and we also have a peak at -1 kilohertz. I think that's pretty interesting. One way to interpret this is that we actually have 2 complex exponentials added together, one with a positive frequency and one with a negative frequency. If I turn this frequency down to 0, at 0 we see 1 peak at 0. If I turn it up, well, that's interesting. When it's at 0, the amplitude's a little bit higher, isn't it? Or the power is higher. And then if I turn it up, that power gets split between those 2 signals, one at a positive frequency and one at a negative frequency. If I keep going up and up and up, watch what happens. It looks like each signal kind of bounces off the edge and then comes back to 0. If I keep going up, I'll go faster, then they bounce off 0 and then go back across. And if I go again, they bounce off the edge and come back. Now, that is one way to interpret it, and that's the way most people interpret it if they're only looking at the positive frequencies and not the negative frequencies. But I like to interpret it a little bit differently. If I start at 0 and I start increasing my frequency, I go up and up and up and up. Imagine that both of these signals, the positive and the negative spike, are going to wrap around. It's the Atari effect again, but this time it's happening for both signals. One of them went off the right side of the screen and came on the left, and the other one went off the left side of the screen and came off the right. If we look at it with a real valued FFT plot, and I disable this float to complex, then, and we do the same thing, then it appears that you have one spike that is bouncing off one side and going back the other way. But the way I like to interpret it is that it's actually the Atari effect. It's wrapping around one side, and it is wrapping around from one side to the other, but the other side is a negative frequency. And then, in addition to that, we have a symmetric frequency domain. So if I look at it again with complex valued FFT, we have a symmetric frequency domain. And anytime you have a real valued signal, you always have symmetry in the frequency domain, because with a real valued signal, there's no difference between positive frequencies and negative frequencies. But with a complex valued signal, a signal can go around the complex plane in a clockwise direction or a counterclockwise direction. So there are negative frequencies that can be different than the positive frequencies. When we looked at both the positive and negative frequency components of a cosine wave, a real valued cosine wave in GNU Radio Companion, we saw something that looked similar to the sum of 2 complex exponentials that have one with a positive frequency and one with a negative frequency. So let's take a look at what happens if we take 2 complex exponentials that are equal in every way except that one has a positive frequency and the other one has a negative frequency. If we add them up, if we do a point-by-point addition, then let's see, we add these first 2. That's 1 plus 1, which is 2. Then we add these next 2. Now, one has a positive imaginary component and the other one has an equal but opposite imaginary component. So they cancel each other out when we add them together. And what we end up doing is we just double the real part, and we end up here on the real axis over here. Now we take the next 2, and you'll notice again we're going to if we add them together, we'll cancel out their imaginary components because they're what's called complex conjugates. A complex conjugate pair is two complex numbers that have the same real part but opposite imaginary parts. So we add these two complex conjugates together and we get a number somewhere over here. And we add these two together, we get a number somewhere around here. We add these two together, now they have zero real part and they have opposite imaginary parts, so we end up right at the origin when we add them together. The next pair added together is somewhere around here. And you'll notice that we started out at 2 and then we kind of zoom past the origin and then slow down as we'll get to -2, and then we'll speed up and zoom past the origin as we get to +2. What we're tracing here, if we were to look at the real axis versus time, would be a cosine wave. In other words, cosine of theta is equal to e to the I theta plus e to the negative I theta. Two complex exponentials with opposite frequency added together, but then we take this whole thing and divide it by 2 because when we add those two together we get out to plus or minus 2 instead of plus or minus 1. So all what we see here is that, in fact, mathematically speaking, a cosine wave is a sum of two complex exponentials. So we can see that, and we can derive that from Euler's formula algebraically, or we can see it just by looking at the frequency analysis of a cosine wave in GNU Radio Companion. When we have our flow graph configured for complex valued signals, and we select a low positive frequency, the signal source produces a series of samples like so, and the FFT sync shows us that we have a spike that is a little bit to the right of 0. But if we increase the frequency, then the spike in the frequency domain moves to the right. If we increase it all the way up to half the sample rate, then the first sample will be here, the second is here, the third is here, the fourth is here. It's going back and forth between 1 and -1. And the frequency domain representation that the FFT plot shows us is a spike, not here at 0 hertz, but way over here right at the edge. And if you look closely, when you have it configured for exactly half the sample rate, you should be able to see a little bit right over at this edge also, because we don't know whether the signal is going around this way or this way. It's the same either way, right? Exactly the same. And this frequency over here is Fs, so the sample rate over 2, and this over here is negative Ss over 2. And it's actually, you can think of it as being both frequencies at the same time. If we increase the frequency further, then we go a little bit more than half a turn over to here. And then the next one is a little bit more than half a turn over to here. But you can think of that as being a little bit less than half a turn in the negative direction. So what we see as we increase the frequency this way, we see it wrap around over to here, and our spike is right there. And this is the Atari effect that we saw several times before, where when we increase the frequency, we go to the right, it wraps around to the left. If we decrease the frequency and it goes to the left, it wraps around to the right. And we can keep wrapping around forever with increasingly higher frequencies or lower negative frequencies, and find many, many different frequencies, an infinite number of different frequencies that are all the same as one another. So for example, this frequency that is here and then here and then here and then here and so forth, we could think of that as tau over 8, or we could think of it as going around this way, negative 7/8 tau, or we could think of it as going around in maybe in the negative direction once and then twice and then to there. Well, what's that? That's negative 15/8 tau. Or we could think of it as going around in the anti-clockwise direction once and then twice, or once and an eighth. So that would be 9/8 tau. We could keep going here and think of any number of integer numbers of rotations between samples that occur, and we can come up with all these different aliases. They're called aliases because they're different names for the same thing. It's one frequency that can go by the name of a different frequency, and we can come up with an infinite number of them, but they're all related to tau, or they're all related to the sample rate. So what I have called the Atari effect, or the wrapping around from one side of the frequency domain to the other, is in fact aliasing. The phenomenon of aliasing is when we consider one frequency by another frequency's name, or we consider the frequency component of a signal as being a different frequency than you might expect. And this happens because the frequency domain is periodic. Anytime you have periodic sampling, then you have a periodic frequency domain. And so if we plot the frequency domain representation, we usually see 0 hertz in the middle, and then f of s over 2 on the right-hand edge, and minus f of s over 2 on the left-hand edge, and we always see wraparound from one side of the screen to the other, one side of the plot to the other. And we can wrap around as many times as we want. If we keep increasing the frequency, for example, we'll see a spike that moves this way and then wraps around to this side, and we keep increasing the frequency, and it wraps around again, and we can keep increasing the frequency infinitely. And no matter how high a frequency we go to, it will always be represented in some way in our little bandwidth here. And this bandwidth is, in fact, our sample rate. Notice that the bandwidth is always equal to the sample rate. And this is one way to state the sampling theorem. Now, the sampling theorem, which you might have heard called the Nyquist-Shannon sampling theorem, perhaps, although it was discovered independently by various people, you may have heard of it stated something like this. Maybe you've heard of it like the sample rate, f of s, must be greater than twice the frequency of interest. And remember that people who are stating the sampling theorem in this way, or something similar to that, are thinking about real valued signals. Real valued signals only have half of this bandwidth. They go from 0 hertz to f of s over 2. You don't see the negative side because the negative side is simply a mirror image of the positive side. And that's always the case with real valued signals. The negative frequencies are always a mirror image of the positive frequencies, so they're typically ignored. They're there, arguably, but they're redundant information. If we were to plot the left-hand side of this frequency domain plot, it would be identical, or a mirror image of the right-hand side. So there's no extra information over there, and people think of it as being that let's say you have a 1 mega sample per second frequency of sampling frequency. So f of s over 2 is 500 kilohertz. Well, let's say you have a signal of interest that is at, let's say 200 kilohertz. Well, that's going to show up just a little bit to the left of center here on your frequency domain plot. And if you increase the frequency to, say, 400 kilohertz, then that's going to show up over here. But if you increase the frequency of interest to 600 kilohertz, let's say you have a signal at 600 kilohertz, well, that's off the right-hand side of the plot. And so to think of this, to think of where it is located really, I like to think about there being a negative component over here. I know it's going to be a mirror image of the positive component, but if I go off the right hand side of the screen, then what I'm doing is I'm going over here. And guess what? There's a mirror image of that over here. And so now, oh, guess what? My 600 kilohertz signal clobbers my 400 kilohertz signal. Let's say there's both being present and I'm trying to sample both of them. Well, in the digital domain, they interfere with each other instead of being distinct from one another. Suddenly, as soon as we digitize them, they are no longer distinguishable from one another. And this is a real problem. And most of the time, this is considered something to avoid, a problem to avoid. So if you have, now let's say that we have a real world, this is an analog frequency domain here that I'm going to plot. Real world analog frequency domain, it goes infinitely to the right and it starts at 0 hertz. And let's say we have some signal here, and then we have some signal here, and we have some signal here, and we want to sample one of these things. Well, let's say we want to sample this one. Then the traditional thing to do is to find its highest frequency of interest and say, let's say we want to capture from here to there. We take this frequency and call that f of s over 2, and we're going to choose our sample rate that is twice that. So our sample rate is going to be f of s. And then we have to filter in the analog domain before we sample. We filter this out, and we filter this out. We filter out all this stuff to the right. In other words, we use a low-pass filter. The frequency response of the filter ideally would look something like this. We would pass these low frequencies, and then we would pass zero amount of all frequencies higher than that. We call that a low-pass filter. Now, it's possible that instead of low-pass filtering, we could do a band-pass filter. And this is something like this. Let's say 0 hertz is there, and again, we have some signal here, and some signal here, and some signal up here. But let's say the signal we're interested in is, in fact, that one, and not this one over here. Well, there are a couple of different ways we could deal with this. One way would be to take this high frequency and call that f of s over 2 and have a much higher sampling rate than we did in the first case. But the other way would be to say that this down here is, or maybe there, is f of s over 2. Now that's interesting. And then this over here would be f of s. But if we were to band pass sample, if we were to have a filter in the analog domain, we're trying to we block this lower signal, we pass this signal in the middle, and we block all signals higher. That's a band pass filter. We get rid of this stuff, we get rid of that, and then when we sample, we have only this represented in our digital domain. We don't have any aliases clobbering each other once we've digitized this signal. This is a completely valid way to sample this signal, and it's called band-pass sampling. We could, in fact, select a band that's even higher than our sample rate. We could select this band up here or over here. It doesn't matter. We can select any of those because they'll all be aliased once they're digitized. They'll be aliased down to baseband or down to the frequencies in the vicinity of 0 hertz. So that's one reason that the traditional way of thinking of the sampling theorem is arguably wrong, because we can use bandpass sampling to have a sample rate that is actually lower than our signal of interest. But another way that I think the traditional representation of the sampling theorem is wrong is because it talks about a frequency, a sampling frequency being greater than twice the frequency of interest. And that is only the case, that doubling there is only the case if you're dealing with real valued signals. I think that a more elegant statement of the sampling theorem, a more elegant statement is to say that the bandwidth described by a digital signal is equal to the sample rate. Now, this is only true if you're dealing with complex valued signals. But isn't that an elegant statement? The bandwidth is equal to the sample rate. And you can see that every time we look at a frequency domain plot, we always see from negative f(s) over 2 through 0 to positive f(s) over 2. The bandwidth described by any digital signal is this complete range from negative fs over 2 to positive fs over 2, or that's the sampling rate. The bandwidth is equal to the sampling rate. Now, if you have a real valued signal, then of course this negative stuff is ignored normally because it's just a mirror image of the positive stuff. So there's no additional information over there. In other words, in that case, the bandwidth is half the sampling rate. But I like to think of the sampling theorem as this. The bandwidth is equal to the sample rate. In digital signal processing, we normally represent the frequency domain in a planar plot like this. But it's not truly a plane. The frequency domain is cylindrical. It's periodic. If you go off one edge, you come around the other side. And this is a fundamental characteristic of all digital signals. Anytime there's periodic sampling, you're going to end up with a periodic frequency domain. And I think of the frequency domain of real value signals as being the same exact thing, except that this is flattened. You still go off one side and come around the other side. However, there's bleed through from the positive and negative frequencies. They're mirror images of each other because they bleed through. So you still go around and around and around, but you also have this bleed through effect. Now, we talked a little bit about filtering in the analog domain, and in particular an anti-aliasing filter that we can use for sampling a particular band of interest. And we've also talked a little bit about digital filtering. We've used digital filters in some of the flow graphs that I've demonstrated so far in this series. And for the homework for this lesson, I would like you to experiment with digital filters that we'll talk about more in the next lesson. Go to greatscottgadgets.com/SDR, and under Lesson 9 you'll find the homework assignment. I hope you'll do the homework assignment, and I hope I'll see you next time for Lesson 10.